Hi everyone. Today we are going to talk about the sleep systems and their important relationship with shear stress in crystals. Understanding how and why sleep occurs is key to explaining plastic deformations and failures in metals. When a material is stressed, means tensile stress, the result shear stress acts on specific crystallographic planes and directions. These are the sleep systems that we talk about that before sleep systems for different structures such as FCC, BCC, HCP. And these sleep systems uh, are the systems where atoms can move most easily. Why? Because they are more packed at that planes, at that directions. Failure or permanent deformation usually begins along these planes because they require the least energy for dislocation motion. We will also see how the critical resolve shear stress or tau CRSS determines when the sleep starts, and at the end of these sessions and video we will go through two example problems to make these concepts crystal clear and practical for you. Okay, go ahead. Okay, a sleep system for FCC, BCC, HCP. There are several important structures that today we focus only on three of them, FCC, BCC, and HCP. What is a sleep system? Excuse me. A sleep system is a crystallographic plane, and within that plane, a directions line, line which dislocations motion or a sleep occurs. For example, in FCC, the plane that we are talking about, that is the family of 111. Okay. So here is the family plane is 111. We show planes by parentheses, but for the family we use this, okay? So it is family plane and it is the plane. So these families have the maximum planar density. So PD is max in that family. And we have family directions that for these family planes, these family direction. So it is family direction that has maximum LD or linear density, if you don't remember from previous videos. So, each plane that had maximum planar densities, and at that planes, which directions that has most linear densities specify for us the sleep systems. Okay. For metals, all metals don't have the same sleep system. The reason for this is that for most metals, the sleep system will consist of the most densely packed crystallographic planes, and within that plane, the most closely packed directions. These planes and directions will vary from crystal structure to crystal structure. For example, for FCC, how many sleep systems we have? We have 12. All of them are primary. For BCC, we have 48 total sleep systems, as you see at this table, but 12 of them are primary. What's the meaning of that? Means another 36 will be excited at high temperature, okay? Or for HCP, totally we have 12 sleep systems, but only 3 of them are primary. So for metals having these two crystal structures, such as BCC and HCP, some sleep systems are often operable only at elevated temperature or high temperatures. And here you see the planes or 111, and you see the directions by the arrows. These directions have the most linear density, and it is the plane. So it is a slip system. What's the meaning of a slip systems? Means if failure will occur because of the shear stress or dislocations movement, some things definitely occur at that planes, at that directions. So because of that, they are so important for us. Okay, back to strength of the materials. When we have the tensile stress, for example, as you see here, only these planes or this cross section is not critical. Maybe we have another planes that shear stress be the maximum or some things. If you remember, for ductile material, the plane that shear stress was maximum is the most critical for us. Or for brittle material, only tensile stress is important. Again, if you remember from Mohr circle or some things, principal stresses is important for finding that which plane is more critical. Okay, we consider the directions of the tensile stress is this, okay? And a slip direction is that direction, a slip direction. What is a slip direction? Remember from the previous slide, slip directions, line, slip plane, and direction that has maximum LD in maximum PD planes. Okay, so it is the slip directions that the angle between the stress directions or applied stress and slip direction we show by lambda. And the normal to slip plane is the green color here. I show by green again. It is this direction, and the angle between applied stress and normal to slip plane shows by phi. Okay. If we have F, what is F prime? F prime is the component of the F in that slip direction. So F prime will be F cosine lambda, agree? And for A prime and A, so it is A prime and it is A, okay? We know that perpendicular to A prime, I changed the color, perpendicular to A prime and perpendicular to A have this angle as phi. So we can conclude that this angle is phi 2. What is the relation between A and A prime? A is A prime cosine phi. If I write the shear stress formula, shear stress means the force parallel to cross-section area, that is F prime here, divide I prime. What is F prime? We told that F prime is F cosine lambda. What is A prime? From this equation, A prime should be A cosine phi. Okay, go to next slide. Instead of F prime, I substitute F cosine lambda. Instead of A prime, I substitute A cosine phi. So we reach FA cosine lambda cosine phi. What is FA? FA means force divide this cross section that perpendicular. So it is the normal stress or sigma. So resolved shear stress or tau R is sigma cosine lambda cosine phi. So here we have sigma, but if we want to talk about the slip system and the slip direction, it converted to a resolved shear stress as sigma cosine lambda cosine phi. Why? Because again, when we have slip systems, if failure happens or dislocations move because of shear stress, exactly at the directions of slip system. So it's very important for us to finding the equivalent stress in that directions, and that directions will be shear stress or resolved shear stress. Okay. In single crystals, there are many slip systems, you know that, with different orientations. For example, for FCC, we saw that we have 12. For BCC, we have seen 48. For SCP, we have seen 12. But some of them are primary, but 12 is important. It means we have 12 different slip systems, different orientations. But the slip begins at the system that is the most favorable oriented. What's the meaning? Means this occurs where the resolved shear stress or tau R is maximum at that direction. So tau R equals, we know that sigma cosine lambda cosine phi. So tau R is sigma cosine lambda cosine phi. When it is max, this TR be T critical, means instead of TR, we have tau CR SS, means critical resolved shear stress when it is maximum. What is the amount of that? This critical resolved shear stress between 0.1 megapascals or 10 megapascals and means that this occurs where the resolved shear stress is the maximum or cosine lambda cosine phi is maximum. The slip system with highest tau R will activate first, means it's the most candidate that failures happens at that direction. So for example, we have 12 directions at FCC. Each of them has different orientation. We should calculate cosine lambda cosine phi for each of them by considering the directions of the applied force. Each of them that has maximum cosine lambda cosine phi, the failure and slip system start from that and will be a more candidate or the best candidate that activate the dislocations motion. So in a single crystal, there are multiple slip systems, a variety of orientation, one slip system for which tau R is highest, means tau R maximum is more than sigma cosine lambda cosine phi maximum, most favorable orientated, that the slip system start from where? Yield strength of single crystal or sigma y, we have sigma y is T critical cosine lambda cosine phi maximum. What's the meaning of this equation? Means that we know the T critical, we know which directions have cosine lambda cosine phi, and by this equation we find which or how much sigma y needed for starting to dislocation or dislocations movement to start. Okay. In single crystal, parallel slip steps can form on the surface as many dislocations move along the same slip planes. If you see these slip planes are the planes that they have maximum tau R. Tau R is max or maybe critical or failure start from that plane. So in single crystals, parallel slip steps can form on the surfaces as many dislocations move along the same slip planes. These steps are visible at the macroscopic scale and sometimes appear at the straight slip lines on the crystal surfaces. When a single crystal's metal is stretched, dislocations move along a specific plane. Which planes have maximum PD or slip system, creating tiny surface steps This appears as parallel slip lines on the polished surface showing the plastic deformation. What's the meaning of plastic deformation? Means dislocation movement, means reach to failure or yield one. Okay, example. The formations of the single crystals. We have we want to check that will a single crystal yield at that slip directions or no? If not, which stress is needed? Which stress means how much sigma needed for that. And we know that critical resolved shear stress at 20.7 megapascal. Okay, it is the directions of the stress. It is directions of slip direction, and the angle between them is lambda. Normal to a slip plane is the green one. The angle between normal to a slip plane and directions of applied stress or phi is 60. So tau r is sigma cosine lambda cosine phi. How much sigma we have? Sigma here, we see that is 45 megapascal. Substitute here, and we find that 18.43. It is less than critical value, okay? So when less than critical value, it means that this single crystal will not yield. But do you remember the formula that we talked about that I told that sigma needed is tau critical per cosine lambda cosine phi. Tau critical, we know that. Cosine lambda cosine phi, we know that. And substitute, and we see, okay, if we have 50.54 megapascal along that perpendicular to this plane or normal stress, we reach to yield because of the shear stress. And it's interesting that 50.54 needed, but the single crystal start to yield because of 20.7 megapascal, means less than half of that. Why? Because slip direction is critical direction for us, and shear stress here is important, not normal stress. Okay? Because the structure is more ductile, not brittle. Okay. Another example is very important, very tricky and challenging question for this part. Critical resolved shear stress from direction cosine for an FCC silver crystal. Considered a single crystal of silver oriented such as the tensile stress is applied along 0, 0, 1. This bracket means direction, yeah? 0, 0, 1 means x0, y0, z1. If x is here, y is here, z is here, the directions of applied stress should be this direction, okay? If a slip occurs on plane 1, 1, 1, all of you know that how find the plane. Reciprocal of them be intersect of the plane. For example, this point, this point, this point connect each other, and it should be this plane. 1, 1, 1. Okay. And in a -1, 0, 1 directions, -1, I want to show that direction by different color. I show by green, for example. -1 means x minus 1. It should be that direction. Yeah. So it is directions of -1, 0, 1. Yeah. And it is initiated at applied tensile stress 111 megapascal. So sigma y is 11 megapascal. Compute the critical resolved shear stress. Back to previous slide, where we have critical resolved shear stress. Critical resolved shear stress will be in slip system direction. Since silver is FCC, has maximum resolved shear stress on slip systems, or the maximum estimate factor cosine lambda cosine phi will be on the FCC primary slip system. What is primary slip system? The family plane 1, 1, 1, that we show one of the planes of this family here, and close path, because of the close path planes or maximum planar density, and the slip direction, it should be 1, 1, 0. Means it is the family directions that we have, that -1, 0, 1 is one member of this family. You know that how we find the family means rotate that, change the sign of that, all of them belongs that family. How we find the family? Each direction that has the same linear density means include in that family or be member of this family. Okay, so this direction and this plane definitely will be the slip system. So if the yielding happen or failure happen or dislocation start to slipping, definitely be at that plane and that direction. So they are the most candidate for a slipping system. Okay, so again, if you remember, plane was 1, 1, 1, and direction was -1, 0, 1. Yeah, yeah, -1, 0, 1. Okay, the angle between phi and plane, it is lambda. The angle between sigma, sorry. The angle between the phi and normal to the plane, it is phi. First, we want to find the lambda. We use this one, cosine inverse u1, u2 plus v1, v2 plus w1, w2 per root squared. u1 squared, v1 squared plus w1 squared times u2 squared plus w2 squared plus omega 2 squared. How we find that? It comes from the dot products, means for example, if we have the directions of the parallel to the planes and sigma directions for sigma, it was 0, 0, 1. It is for sigma, yeah. So it is this one, u1 is 0, v1 is 0, w1 is 1. And for the plane or the directions to the planes means -1, 0, 1, means u2 is -1, v2 is 0, w2 is 1. How we find this angle? Remember from dot product. If we have A dot B, means two vectors multiply each other, it should be absolute value of A, absolute value of B, and cosine, for example, is lambda. So what is cosine lambda? Means dot product in numerator, divide per absolute value, and you see here absolute value of that. Okay? So substitute here and we find lambda. Lambda is 45 degree. What is lambda? The angle between applied stress and parallel to the plane. What is parallel to the plane? Means directions that we have. Another angle that we are looking for that is phi. Phi is the angle between sigma and normal to the plane. We know the plane. What is the plane? 1, 1, 1. I say that when we have a plane as 1, 1, 1, the direction perpendicular to this plane be same numbers, but only direction should be 1, 1, 1, 2. So here again use these equations, but this, so U1, V1, W1. It is U3, V3, W3. Substitute in this equation and we find V. What was T critical? T critical was sigma y cosine phi cosine lambda. We know sigma y, we know cosine, we know phi, we know lambda, substitute here, and we find the critical resolved shear stress at that direction. Can we say is it a good candidate? No, we cannot say. How? Because we have another 11 direction. It is one of the directions that we have in FCC, one of the primary. We should compare all of 12 primary slip directions that we have. Each of them, the maximum should be at the most candidate that the slip starts at that direction. So that wraps up to our discussions on slip systems and the critical resolved shear stress. We saw how the orientation of the slip plane and slip directions controls when a single crystal begins to deform and slips, and we worked through two examples showing how calculate the applied stress needed for yieldings and how to find the critical resolved shear stress for given material. If this video helped you to understand the topic better, give it a like, subscribe for material science lessons, mechanical properties, and leave any questions or comments that you have, please. I always read them and try to respond. Thanks for watching the video and see you again in the next one.